underground. Save some time, don't just dig around. Pop, pop, avoid a hit. Know where it is before you split.
Welcome to the Subsurface Solutions Locator Bootcamp, where you're going to become the master at finding the location of underground utilities.
Hey, what's up? I'm Michael Faraday, and I'm excited to show you the wonders of electromagnetism and how we use it to find underground utilities. It's pretty cool stuff. Let's dive into the basics of electricity.
Before you start spraying paint and flinging those flags, there's 5 things we should cover first. And the first one today will be about electricity. Basics of electricity is going to help you with locating for sure. And then grounding. How do we complete the circuit? You got to have a good ground, right? And so after that, we apply our signal, and we'll go over how you apply your signal onto certain facilities and targets. And then how do we receive that signal with the receiver? Just like a radio station, we got to be able to tune into it and receive it. And how do we pinpoint the line we're trying to target? And then how do we check or locate for accuracy? I call that checking your mirrors. You check the 5 different checks and balances on the screen of the receiver to let us know if we have an accurate locate or not. To understand how we can find underground cables and pipes using electricity, let's start with the basics of electricity. Electricity is all around us. It's powering our homes, our gadgets, even our cars and trucks. So what is it exactly? Everything is made up of atoms. They're tiny particles that have a nucleus, kind of like the sun, and electrons like planets circling around. That movement is called electricity. So some materials like copper let electrons flow freely. That's called good conductivity. And so others like rubber don't let electrons flow easily, and those are called insulators. Gas companies will use insulators to insulate electricity from flowing, so it will stop corrosion. But electrons, they flow, and there's 3 things involved. There's current, which is how fast the electrons move. There's voltage, that's what pushes them. And then there's resistance, that's what slows them down. These 3 things are connected, and they can't change without changing another one. And so if you look at Ohm's law, volts is over current and resistance. If you divide volts by current, you'll get resistance. If you divide volts by resistance, you'll get current. And if you multiply current and resistance together, you'll get volts. So if we look at our transmitter, you'll have a voltage ohm key at the very bottom, and you're able to see the milliamps, the volts, and the ohms. If you look at the 20 milliamps, it's requiring 2 volts in order to get that 20 milliamps to go out because of the resistance. We have 100 ohms of resistance. Well, if we take the 2 volts and we divide that by 20 milliamps, we'll get 100 ohms. And if we take the 2 volts and divide it by 100 ohms, we'll get 20 milliamps. Ohm's law shows us the push, the voltage, the flow of the current, and the resistance as soon as we hook up our transmitter. You should look at your voltmeter on the screen of the transmitter. Imagine it kind of like flowing water through a hose. The current is the flow of the water, the voltage is the pressure pushing it, and the resistance is the size of the hose. The smaller the hose, the more resistant it is, means less flow. But if you increase the voltage, you can get the flow to go more. You have the same amount of resistance, but you have more current flowing. And so Alessandro Volta invented the electric battery. His invention provided a steady source of electric current back in 1800. It could be crucial for later experiments in electromagnetism, electronics. His work laid out the groundwork for understanding electricity and creating devices that could generate and sustain an electric current, just like our cable and pipe locators.
Why did the electron break up with the proton? Their relationship was too positive. Haha, LOL.
In 1831, Michael Faraday figured out that changing magnetic fields can produce an electric current. He invented the first electrical generator and discovered electromagnetic induction. Faraday's work on electromagnetic induction is fundamental to the operation of transformers and generators. This principle is also key to the way radio transmitters generate radio waves by converting an electric current into electromagnetic waves.
Yo, electricity and magnetism are like 2 sides of the same coin. When you run an AC through a wire, it creates a magnetic field around that wire. So in summary, electromagnetism is the beautiful dance between electricity and magnetism, a dance that has powered the modern age cable and pipe locators. May the magnetic force be with you.
In the 1860s, James Clerk Maxwell formulated equations describing how electric and magnetic fields are linked. and predicted the existence of electromagnetic waves, including radio waves. His work laid the foundation for understanding radio waves as parts of broader spectrums and electromagnetic radiation.
I linked electricity and magnetism so well, they're now inseparable.
In 1887, Heinrich Hertz demonstrated the existence of radio waves. His experiments proved Maxwell's theories correct by producing and detecting radio waves in the lab. This was the first time electromagnetic waves were shown to exist and be measurable, directly leading to the development of wireless communications.
I discovered radio waves, so you can listen to music and locate cables and pipes. Crank it up until it hurts. Come on, baby, make it hurt so good. Locating using waves, just like you should.
In the 1880s, Thomas Edison is more famous for his work for the light bulb and distributing direct current to homes, but he also experimented with wireless communications. Edison's work with electricity and communication technology helped lay the groundwork. He patented the system of wireless telegraphy in the 1880s, which was an early form of wireless communications.
Direct current, DC is the future. Steady, reliable, just like me. No funny business.
But in 1887, Nikola Tesla developed alternating current, which could travel longer distances much more efficiently than DC. Tesla's AC could be stepped up with higher voltages to travel the long distance and then step back down for safe distribution to homes and businesses. This was done with transformers, which only work with AC due to the changing magnetic fields. Tesla's AC eventually won out over Edison's DC.
I took his clunky, slow-moving DC and made it bounce with sass.
Tesla also developed theories and devices for transmitting electrical energy wirelessly, and his work on high-frequency currents and radio waves contributed to the development of early radio transmitters. Collectively, all these guys' discoveries and inventions formed the building blocks that enabled the development of radio technologies used in cable and pipe locators. Modern cable and pipe locators generate electromagnetic fields that interact with the buried cables and pipes, making it possible to detect their location without digging. By understanding and applying Ohm's law, we can safely and accurately locate underground utilities today. So here's the first receiver that we know of. In 1910, in Germany, they took a bunch of copper wire and wound it around a roof truss, and that worked as an antenna, picking up the electromagnetism, and that's where electromagnetic locating was born, in theory. That's what we think, I guess, maybe. That electromagnetism can be picked up by witching sticks. So if you haven't fooled with witching sticks before, take two wires, bend them in an L shape, hold them loosely in your hand, and hold them perpendicular to the target line that you're trying to pick up. If you're doing it for the first time, do it on a power line. A power line, especially a primary power line, has a large magnetic field around it. They'll move and want to magnetize to that magnetic field. That's what's creating the movement, is the magnetism. And so we're advancing that primitive technology into a cable and pipe locator, and we're able to use an identifying frequency with multiple antennas in the receiver that will receive that signal, that magnetic field, and be able to measure it, to giving us a depth, a current measurement, and other checks and balances. The most accurate way to locate underground utilities is called active locating. Active locating is the process of applying an electrical current, identifiable frequency, to a conductor, and that current is going to want to flow. It's going to want to move those electrons, and the voltage is going to push them down the line. And then the resistance, depending on what the material type is of the utility you're locating, is going to resist that current traveling down the line. So the best way to approach a locate is to think, how does electricity want to flow? It wants to flow to the path of least resistance. We want the electricity to flow to the mass. We want it to flow to the bigger lines, the bigger pipes. And so we start at the house, the opposite of how the product's getting to the house, we locate. Let it flow to where it wants to go, back to the main line. So question for you. What is the first step for locating? It'd be maps, prints, and as-builts. You got to consult what information you have and compare it to the dig area that's already out there. Hopefully the excavator has white line the area he plans on digging and put some white flags down. So you can take that and compare them to the maps and prints you have. And then you know exactly what needs to be located in that area. And you also can compare that to the above ground features, all the landmarks that are around you, maybe the pedestals, the hydrants, the valves that you can hook onto to apply your signal onto the lines you need to get located. And so when you're doing a locate, it's like putting a puzzle together. You always start with the outside edges. You start in an isolated area and you go into the mass. You go into the congested area. Never try to start in the congested area because it's going to be much more difficult to identify and figure out which signal you should be following. Take the prints and then figure out where you need to hook up, apply your signal, receive your signal, get everything located out, verify your signal's good by your checks and balances, which we'll cover later, and then put your paint and your flags down. So your prints could be paper, they could be as-built, they could be line cards, or they could be a more advanced GIS system. GPS accuracy is getting better, the prices are coming down. We're able to actually use the GIS prints to relocate lines. Here's a nice GIS system with aerial photography in high resolution where we can actually zoom in to the lines that have been installed, the power lines in this case, and we're actually able to see the depth readings as well. You could pretty much relocate just following that line out using a GPS unit with the same kind of accuracy. And so, again, think of it like putting a puzzle together. You start from the outside, you work your way into the middle. We're applying AC current, that's oscillating current. That means it moves back and forth, as opposed to DC, which is just constantly traveling in the same direction. And that AC is the frequency that we're applying. The rate of the alternation is the frequency that we choose on the transmitter. So if we choose 512 hertz, that means it's traveling or oscillating at 512 times per second, going back and forth. And that's what's magnetic. That's what's creating the frequency, the magnetism, the magnetic field that we're able to pick up with the receiver. So if you took a straight DC battery and you had a wire on it and a compass next to that wire, and every time you unhook that wire and hook it back up again, you're creating a fluctuation, an alternating current. If you did that one time per second, it would be a 1 hertz frequency. And so the lights above our heads are oscillating at 60 times per second, 60 hertz frequency. So we're able to go into the receiver, choose 60 hertz, and should be able to pick up a signal, pick up the current that's already present on the line. But that's passive locating. Active locating is actually setting up a transmitter, putting a ground rod in the ground, applying your own frequency, identifiable frequency, that's not going to interfere with other frequencies that are in the atmosphere, and we're able to receive it. The next session, we'll talk about your rods. We'll talk about your ground rods. We'll go from electricity basics to how to apply that electricity. How to ground your system is very important.